Hey everyone, so we just finished talking about kinematics in a rotational section, and I even showed how we can kind of compare our new equations for rotation to the equations that we've already used in the kinematic section. For every equation from there, the the annoying x equation, the timeless equation, the acceleration equation, we have a rotational version of it. And I also showed how we could take linear values like velocity, position, and acceleration and get an angular version of that. I even talked a little bit about forces and mass and how that relates when we start rotating. But I wanted to kind of talk a little bit more about torques, and in particular, torques in the concept of what's called statics. Now, we've already talked about objects that are in equilibrium, and we've already said that when an object's in equilibrium, the sum of the forces are going to always end up equaling zero. That if we have forces in the x direction, they have to cancel out, and all the forces in the y direction have to be balanced and cancel out. This actually, though, tells us that the object is only in what's called translational equilibrium, meaning that it's not going to be accelerating left or right or up or down. Now, just for simplicity's sake, I'm just going to say at rest, but remember that when an object's in equilibrium, regardless of whether it's rotational equilibrium or translational equilibrium, that could also mean moving at a constant speed, but it's just a little bit easier for me to say at rest rather than at rest or moving at a constant speed. So just keep that in mind. So again, object's not going to accelerate left or right, up or down. Basically, it's just going to remain still. Now, what about in this case? So I have a seesaw. I have a mass on one end and a mass on another. And I can ask you, would this be in equilibrium? Would this be something where it would stay balanced? Now, if we look at forces, we would see that this actually would have the forces balanced out. We have two masses on either end pulling down with a force, and very likely, even though it's not shown, there is a normal force that's going to push up, and we can pretty much assume that it's going to push up with the same force that these two are pushing down. So we have 10 newtons and 10 newtons, so this would be pushing up with 20 newtons. However, if we actually try to attempt this, we would automatically see that it doesn't remain still. It actually does tilt. In fact, this side will end up tilting down. So what's the issue? Well, we've talked about, we're looking at it only through the realm of forces and how it's translationally in equilibrium. What we have to do is open up our definition of equilibrium to also include the concept of rotating, whether or not the object is rotating or not. So if an object's in rotational equilibrium, basically it's not going to be rotating clockwise or counterclockwise in some form. Now, I can ask, well, how would we know if an object's in rotational equilibrium? Well, you can probably guess that if in the other case we said that the forces had to balance out, then we could see that the torques are going to end up having to balance out. So this is basically going to add in a new equation to our roster of equations. So let's see. No, I didn't write it here. If you recall, when we had an object that was in equilibrium originally, you would always start with sum of the forces equals zero. Sum of the forces in the x direction equals zero, or the sum of the forces in the y direction equals zero. Well, now what we're going to end up having to do is also include this next statement that the sum of the torques are equal to zero. Now, the reason why we're going to have to take this into account is because of two different types of questions. The first one would be questions where they're wondering where certain forces need to be placed. Now, if you look at the equation for sum of the forces, in the standard equilibrium, we can already see that that's something that can't be answered with forces. The equation F net equals zero does not tell us locations of forces, just the values. So right off the bat, we can already see why torque would be ideal in that case, because torque is force times distance or position. Now, the other type of question that you would see is a question where you are not given enough forces. And you'll see what I mean about that in a second. But in that case, you would end up finding that, hey, I can't use some of the forces, so let me switch over and do some of the torques. Now, just to kind of reiterate some things, like what is torque? I've been saying I kind of mentioned it a little bit in the last videos, and I've been using the phrase willy-nilly here. But just to kind of briefly explain what a torque is, it's basically a force that's rotating. That's it. So just like how angular acceleration is for the how much it's increasing its rotational speed or decreasing its rotational speed, uh, basically torque is the same thing but for force. So the only way that we can get torques is by having a force applied some distance from a pivot. Now, like I said, I already gave this equation before, but I want to go into a little bit more detail because I did sort of breeze through the equation. I think you saw it, but I didn't go into too much detail with it. Now, there's three different factors that affect the torque. How far away you are from the pivot. What you can do is you can go to your house and try and open a door first at the very edge where the doorknob is, and then try to open it really, really close to the pivot. You'll see that in order to open the door the same amount, with the same amount of, I guess, effect on the door, having it swing open the same amount, you're going to have to exert a much greater force when you're really, really close to the pivot, because of the fact that the distance is really small, meaning in order to get that same torque, the force is going to have to balance out with it. Obviously, the second factor would be how strong the force is. Again, you can test this out yourself, opening the door. Open it with a little bit of force, open it with a great amount of force, and you could see that there's a massive difference in how the door opens. Now, there is a third one that you might not have thought of, but it's the angle that the force is acting. So this one's going to be a little bit hard to do on the door, at least having a force acting on at an angle, mainly because the hand almost naturally pushes it perpendicular. But what you can do is try pushing onto the door into in the plane. So if this is your door, this is the door hinge. If you push on it like this, you get no rotation. This is something that's impossible to rotate. You need at least a force that kind of goes into the side, that moves at some angle in order for us to get rotation. And in fact, we end up getting our greatest torque when the force that we exert actually acts perpendicular to the object. So here, I can see that if I act at an angle of 0 degrees, this is going to give me 0 torque. But if I act at, pretending this is 90 degrees, I'm going to end up getting maximum torque. Well, what trig function do we have that is 0 at 0 and a maximum at 90 degrees? So our full equation for torque is going to be RF or RF sine theta. Now, when you do a problem, you have two choices to use an equation for torque. If the force is acting perpendicular to the beam, then you can use RF for it, because this is for a case where the position and the force are acting perpendicular to each other. So what are some examples of this? A door with a force being acted on like this, so that's perpendicular. You can have a wheel with a force being pulled down like this. That's also perpendicular because this is the beam, this is the beam. So those would be all perpendicular scenarios. If, though, the force is acting at some angle, then we have to do RF sine theta. This sine theta is actually meant to try to find that perpendicular component. So perfect examples of this would be something like that, where I'm pulling up and at an angle. So we would have to use sine theta so we can get this vertical component. You don't have to worry too much. Like I said, it's really what you're going to look at is, am I at an angle or am I perpendicular? And you can simplify the perpendicular ones to just RF. All right. So The setup for torques, when we do like some of the torques, it's going to look very similar to what we did with forces, and that's pretty standard. It makes sense because torques are related to forces. But again, there are a few key differences. First, there's the fact that position of the forces matter. It matters where and how far it is from some pivot point. And just like with forces, we're going to have to define some sort of positive and negative direction. Now, for the most part, there were two different ways you could define positive and negative. One way was you could have said like anything going up is positive, anything going down is negative, or right is positive, left is negative. You could have also just kind of chosen whatever direction you want, or you could have done what I had mentioned in the dynamic section and made it so that the direction of the acceleration is the direction of positive. Either way, you defined a certain direction as a positive direction, and then you had a certain direction as negative, so that when you did some of the forces, you had some values that were positive, some values were negative, and they would end up canceling out. We're going to end up having to do the same thing here, except instead of talking about up and down, we have to remember that we're talking about a rotation. So imagine this. So I have a beam that's going to pivot in the middle. If I apply a force here, and I apply a force here, are these in the same direction? Well, forces-wise, yes, they're both going up. But when it comes to torques, if this thing is fixed at this point, me pulling up on the right-hand side is going to cause the beam to rotate in a counterclockwise manner. But this one, pulling up on the left-hand side, is going to cause it to rotate this way in a clockwise manner. So while their forces are in the same direction, their torques are in opposite directions. So we would just have to define, we would have to figure out which ones are going clockwise and which ones are going counterclockwise, and then define one of them as being positive. Again, doesn't matter which one. You can choose. You could do the same thing as I mentioned before, where instead of the direction of acceleration, it's the direction of angular acceleration. But for the most part, as long as you're consistent with your signs, it doesn't really matter. But that's the key thing, is to remember that the direction of the forces don't matter, it's the torque. The nice thing about this is you can actually test this out yourself by use your pencil or pen as the beam, put your finger wherever the pivot is, and then apply a force in that direction, and you will see it rotate a certain direction. Now, typically, clockwise is usually going to be defined as positive and counterclockwise is negative, but again, it's whatever floats your boat. No one's really going to hassle you. All that really matters is that you're consistent. If you have some forces that are clockwise, some torques that are clockwise being positive and other torques clockwise being negative, you're going to end up having a bad time. So here's your first question. Pause the video, work yourself, and we'll go over in a second. All right. So the first part says, determine the torques caused by the two masses individually. So for each of these, the force is going to be acting perpendicular to the surface, so we're just going to use FR. Both of them have the same force of 10 newtons. The one on the left is acting at 2 meters, so it's going to have a torque of 20 newton meters. And then the right torque is going to be 1 meter, so it's going to end up having a torque of 10 newton meters. Now for part B, it wants to determine the net torque on the object. So what we're going to end up doing is, well, we would want to kind of add to this. So we would draw a force. These are the directions. This is where it's going to be pivoting around. So this going down is going to cause it to rotate this way, and that would be counterclockwise. This is going to rotate in the opposite direction, so that's clockwise. So I'm going to end up subtracting them. Doesn't matter which one I make as negative and which one's positive, as long as one of them is negative. So the net torque's just going to be 20 minus 10, which is going to be 10 newton meters. And because I made the left one the positive, then that's going to be counterclockwise since I got a positive answer. All right. Here's the next question. Pause the video, work stuff. I'll go over in a second. All right. So let's see. They want to know where should the 5 kilogram object be placed. So again, this kind of goes back to what I was saying about how uh, finding the location of a force is where uh, torques really come into play. So because we know that it's balanced, we know that the sum of the torques, torque on the left, torque on the right, is going to be equal to 0. So that means that the torques have to be equal. Well, just like before, I'm going to use FR. So on the left-hand side, we have a 20 Newton object acting at a distance of 3 meters. And on the right-hand side, we have a 50 Newton object acting at some unknown position. So solve this, and I get that it needs to be placed 1.2 meters away. So it's going to be 1.2 meters away from the pivot. And that's about it for now. There's another aspect to the statics that I'm going to talk about. I'm going to save that into another video. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.